So it seems like a very simple thing to do. But let me share the screen as well, right? So you don't see anything. Right, that's the device, entire screen. All right, yeah. All right, so you should be able to see everything. Now, let's look at our dates again. Remember that there's a final project is due when? Friday, right? So let me see again. How is it? Do we need an extension or do we don't? This one here, right? Let's take a look. So Friday, do you want to go a little bit over that, or is it okay? It's okay.
I think I'll manage.
You'll manage. It's not that hard. I don't think it's that hard. Right. So it's relatively easy. Some just couple gotchas. Okay. Now, so we stay with Friday again. You can. I mean, if you submit it late, it's gonna be okay during the weekend. You to be able to submit it, right? So it's okay, right? So it's not a hard deadline. Now, so we go back to our main topic today. All right. So we go to string searching. And last week we looked at the parsing algorithms for different structuring text. Now we actually we'll go look at seemingly simpler problem, but it's also extremely, how should I say, widely applicable problem of finding something smaller and a bigger. So finding a needle in a haystack, right? Or finding a substring in a string. And again, it seems like extremely simple solutions, right? And of course, I think all of you can come up with a brute force solution to this, but turns out that there are actually improvements possible for this string searching. And the main takeaway from this lecture will be that, as always, the answer depends. Depends what you're looking for, what kind of substring you're looking for, and what kind of what's your search space. There will be different algorithms applicable for this problem, right? So we'll look at Knuth-Morris-Pratt, we'll look at Boyer-Moore, and maybe we'll get to Karp, maybe. Let's see if this link is correct now. I added some changes here. It should be correct. Let's double check. And where's my picture? No, where's my picture? It's not. Oh, yeah, there it is. Yeah, big picture. I just had the huge picture, right? Using the new models, of course, you can put nice little text, right? Maybe let's make it a little smaller. Right, yeah, so this guy here. Yeah, so looking for a needle again in a longer string, right? And of course, maybe, maybe find multiple matches, right? Depends where we start, right? Maybe have some false starts, right? So again, so that's the essence of the problem, basically, right? So this is, if you don't have a Python working, you can run it locally. I mean, you can run it in a cloud column. So this is a Google Colab version, right? Of course, you can run it locally as well, right? So I will be using my local notebook, right? Here, right? Same thing basically, and maybe make it a little smaller, right? I'm not used to this size screen, right? Let's see what the fonts look like. Oh, fonts look horrible. Yeah, okay, maybe now bigger, right? I will make bigger. Can you see this? Yeah. All right. So let me actually rewrite this. So I'll put what we have: MIT, Harvard, Oxford, right? Maybe a little bit bigger, right? So MIT, Harvard, Oxford, and 2, right? I'm not counting the letters, but okay. So again, of course, so in essence, we are gonna see. We know already Python has this, right? So find index, and actually let's do right find text. I think R find, right? R index, right? So because we have two matches like here and here. Now we put a question mark too, right? Right. So of course this is just extra strings. So should be somewhere where it should be. It should be like around 20 something, right? I don't know. Looks like around 20. We'll see. So and where they make. Oh, I have comma somewhere. Oh, there you go. It's a tuple. Yeah, we're getting. Yeah, so now we get tuple 23, right? And 27 here, right? And of course, if I added some extra RTUs, of course, we won't catch those, right? Right? Those will be, we don't have a, well, We have 23 here and 38, the right side is here. So of course, another question is, do you want all catches, right? And so, well, those who know Python know how we could do this, right? How do we count all catches? Of course, we could do also regular expressions, of course, right? But in this case, we could start looking from the first find. We find something, we keep looking, and then we find the other finds, right? So that's another approach. So, but let's see how do we do this with a loop, right? So we have our needle RTU, and again, I will be going to this. I'll update my string, right, to something like this, right? So we have our indexes, right? So how do we find all of them, right? So while index, right? So we can do this, right? So here's an approach, basically, right? So this is actually how you could solve this problem of finding all indexes, right? You have some sort of container, right? You know, we always saw. So we start with a blank container, right? On classical approach, right? Many problems. You need to store your results, right? And you just go through service 0, right? And you check, right? Index, do we find it? So if it's not -1, we append it. We know we found the needle. And then what we do is, so this is the kind of cool part. So this is efficient. So this way we do not find the same something again, right? We start looking from the next index, right? So that makes sense, right? So plus equal 1, right? So we found it, and then we start looking one letter after, right? So we find it here, right? We'll find it here, and we'll start looking at the number letter T. So already, hopefully, you can see that this is not extremely efficient if you can think of some ways of optimizing this, right? Because we're just moving this window, right? We're moving this window, basically. Maybe I'll make a nice little picture. I should probably like a picture for this. Again, I'll do a paint, right? Or maybe I have some slides also from this, but basically paint will be better, right? So we have our string, right? So we have, abracadabra, right? Abracadabra, right? God, right? And we are basically, abraca, right? And we're looking for, let's see, abraca, right? We're looking for, let's say, RAC, right? So we're looking for RAC. That's our needle here, right? So we keep moving it, right? That's our first watch, right? And then we have our second check, right? RAC, right? And then we move the sliding window approach, right? Right, often used, right? So this would be the classical way of solving this problem, right? You just slide the window, right? And you will see that this actually is, yes, this is what we do in many approaches, but it's not the only approach. There are other ways of solving this problem, you will see. But it's a question, of course, how much to move. Here we find it. And of course, the issue is, well, we are sort of, we delegated the responsibility for finding things to Python, right? So whatever Python's approach is, right, it's basically up to them, right? So Python used pretty general one. I forgot what it's of course, it's usual. It's some sort of hybrid approach, right? It'd be interesting if somebody wants to go more research actually exactly which algorithm Python uses, right? But again, of course, it is more generalized because we don't know, Python doesn't know what kind of strings you're going to be looking, what kind of patterns you're going to be looking, right? So again, so this issue is, again, when I'm saying different type of patterns could be, for example, very common way is looking through DNA, right? You have only 4 different letters, right? G, A, T, C, right? Those who know your biology, right? So, but you have these huge strings, billion, million long strings, and you need to be very efficient, right? So with you have very limited, so to say, alphabet. Only 4 different letters, but very huge search space, and maybe looking for pretty big sequence as well, right? So, and of course, you're looking for classical approaches, searching for something in a text, right? But again, pretty much any bioinformatics, legal discovery, of course, search. I mean, we are doing this all the time, right? So looking this all the time. Now, but okay, so let's start with this. So let's see how many indexes we'll find. We find So we find 4. So this approach works. Again, so you can use this recipe, of course, to find indexes, right? And we can check for indexes. We can check if it is, yeah, and of course it is indeed, right? Index plus length of the needle, right? And we see that, of course, it'd be shocking if there was no RTU, right? So, right, so it works, right? Of course. Now, so let's try to implement ourselves. So what we're going to do is let's implement this ourselves, this brute force approach. So we have text and needle. So, well, for I in range length text, right? So we could use enumerate, of course. This could be, we could write this as enumerate. And basically, but this is more like C-like style, right? And we check whether current window, right? So we check whether current window, right, matches the needle, right? And the slicing in Python, slicing makes this thing very easy, right? We know what the length of needle is, right? How long we should slice, and we check. And if we find a match, so this is our find method, basically. This is how we could do it, and it should find 23, I hope, right? Let's see if it works. Hopefully there's no off by 1 errors, I hope, right? Right, so let's see, indeed 23, so it works, right? And we could, of course, keep checking, right? So now let's do this without slicing. Let's even make this even, how should you could make this code, the pseudo code, transferable to other languages which don't have slice, right? So this would be something you would do this, I don't know, 1990s, maybe with a nice method. This is extremely C-like implementation, by the way, right? You know, so we have a range, we have length of text, right? So notice another thing, we calculate, we don't need to go to the very end, right? We have offset, we don't need the, you know, at the very end, at our window, right? We don't need to check here, right? No need to check here. We only need to check here, right? We don't need to do it here. We only need to check here. This is our ending stop, right? Right, RAC, right? You will need to find this, right? So we don't, that's why we have this offset, right? And then you have a range and needle. So this is checking every letter whether it matches, right? So we check each character 1 by 1. So this is actually what's happening underneath, right? In a low-level language like C, of course, this is what you have to do. This basically low-level check, right? So if there's no match, we break because we basically did not find it, right? We break out of the loop, meaning we return -1. Meaning it's a fail, right? So we break means we failed. We failed. Yeah. So no need to continue. No need to continue. Right. So continue inner loop, right? So again, so this means we advance it 1 by 1, right? If at any point in this checking this substring, I mean this window, right? If we don't have a match, right, then we return. So again, so what, and of course, now the question is what's the complexity of this code, right? You have 2 loops, right? And it's relatively easy to calculate, right? There's a constant check inside, and you have 2 for loops. Well, what does this one depend on? Well, it depends on 2 things, text and the needle, right? Length of text, length of needle. But of course, text should dominate, right? Even if the needle is huge, right? You can, of course, if it's very close to length of the text, right, then it will degrade to just 1 loop, right, in some extreme cases, right? Or if it's also alternatively, if it's very short, right? So the issue is if they're both, if the length of text is long, but the needle is, I don't know, 1/4, it's pretty long itself. That's when you get these double loops, right? That's when you get the worst case scenario, right? It becomes quite inefficient. You're moving this 1 by 1 when actually you could possibly skip some steps, right? And again, there is a, so it turns out to be, so M and N, right? So this is complexity is M and M technically, right? So again, if you have very short needle, right, it'll be basically length of the text, right? And now we'll see, can we beat this, right? Can we actually improve it, right? So we'll start with Knuth-Morris algorithm, and I try to put a picture, and I can't do this picture unfortunately doesn't work, right? I had a nice picture prepared, but it's not a nice steampunk picture. But idea is this. If you know already some characters, what we're going to see. So we prepare before searching, we prepare in some way. Maybe we build some sort of data structure. We can build some special called so-called automaton or automata, right? To help us process our text and see when the mismatch is, how much to skip ahead, basically. We will know by doing some pre-processing on the needle, we'll know how much to skip ahead when we're going through the whole big string. So that's a big idea, right? So when we fail, we'll have this prefix function to skip. Again, so there's two approaches. We could use this prefix table, or you can use the actual automaton, actually, right? I think that the example, right, example shows using a table because it's slightly easier. So what happens is, but it's a two-step process. So the complexity turns out to be m plus n, not m times n, but m plus n, right? Because why? Because we spend some time preparing the needle, processing the needle. That's going to be linear for that needle, plus linear for the actual string processing. So this is going to be, in general case, quite efficient, right? More efficient than the brute force, right? But kind of leaving question open, can we do better in special cases, right? So we prepare this table, right? So we prepare a fail function, right? RTU. So in this case, it's a very boring function because, well, each letter is by itself, right? So let's see what happens if I do something like this RT, right? You see what happens? So okay, that's the core idea. Core idea is you start failing, you get RT, right? But you fail, right? You have to start over. But if you get to this letter, you can keep checking, right? If you failed, you don't have to move forward as much, basically. You know exactly how much you should skip. That's the core idea. Maybe if we have time, I can show that in the course materials. We have some visualizations for this. Let me see here if I can find it. Be great to see. And also, I have some materials at the end of this. Princeton has it here, but it's actually not visualization. Do we have it? Oh, here we have it. Yeah, actually, we do have it here. I can show it to you. Yeah, it's still, well, I hope it still works. Nope. Yeah, it's old. Yeah. We are going to say we are going to accept the risk and continue. No SSL. Oh, the URL is dead. All right. University of British Columbia. Unfortunately, it is gone. Right. So we unfortunately there's no cool visualization. Maybe if you find a good link to this, definitely send me and I will include it in materials. Okay. But yeah, so basic idea is we build this table, right? And then again, in this case, all letters are same. There's no repetition. Of course, it's going to be basically 0, 0, 0. So what this means is, of course, you'll skip ahead completely, basically. Let's see if we have failed. Right. So there's a paper by, of course, Knuth is probably the most famous computer scientist still alive, right? Donald Knuth. He wrote this huge Bible for algorithms, right? He's still writing it, right? He's, I think, he's over 80. He's like 85 now, but he's still at Stanford, right? And so he still does some work. A side anecdote, of course, he's famous for answering emails in batch mode, meaning you send him emails and he'll answer maybe 2 months later. He'll just do it one day, basically, just process afterwards, right? He doesn't do it, every day. But it's very efficient, efficient algorithm, right? So, okay. So yeah. So again, I mentioned this again. So ABAAA, right? You can see here again. So if you're getting some matches, right? So idea is that we slide just a little bit. Okay, so we build this table. Among the search is basically text needle, and we supply the table. So if you don't have supply table, we build it, right? So this, of course, this has build. So building table has complexity. ON is where n is length of the needle, of course, right? So then, of course, here, while length of text. So idea is this. If we find it, right, we keep checking each letter by letter, but only different. So it's same as brute force, but the only difference is we have this cheat sheet. This table tells us if we don't have, if you don't find it, basically, oh, sorry, right? We skip ahead. So we skip ahead. We skip ahead, right? So we know how many. That's the core idea, right? So let's search. It hopefully still works. 23. So it works, right? But again, in this case, since we don't have any repetition, it basically will skip. Let me see how it will skip a table, right? For the letter, right? You know, of by one, right? We check the letter, right? And then we skip it. Otherwise, of course, we go one by one. So that's a core idea. So J, right? We keep checking on. If we don't find it, basically we go ahead and skip ahead, right? So we can use timing search, but let's look at the question of can we do better? And the question was kind of interesting is, can we actually beat linearity? Right, meaning you have to go through, do we have to go through all the string? And that might seem like a very silly question, right? I mean, you obviously have to go through all the string, right? But it's not true, actually. In special cases, of course, again, not in general case, but it turns out for many strings, we don't have to go through the whole string. Kind of, on what's the approach? It is to go reverse. That's a very interesting approach, and this Boyer-Moore algorithm is kind of cool, right? Actually, very cool algorithm, right? And actually, I didn't manage to get a picture of what Boyer-Moore might have looked like in the 1980s, right? Same picture, right? But he actually has. I hope this string. I hope the author. I think he's hopefully still alive because he wrote this in the 1970s, right? He has a really nice site, and I'll show you the idea. This is a really nice visualization. So we have an example. That's our needle, right? So here is, right, S, right? So we start looking, right? So one of the core ideas is this. If we get, okay, so we have here is S. We check not first, we check last. Why? Well, let's see. We're looking, this is our example, is our needle, right? If you find S, well, is S in our needle at all? No. So we are completely safe to immediately skipping ahead. So that's one of the core insights. We can immediately skip ahead. So meaning, if we get a bad letter here, we can immediately skip a huge chunk ahead, basically the length of needle. And that's like an easy win, right? So because again, you're guaranteed, right? So because there's nothing here, no matter how perfect, if it's example S, right, it would not help, right? So you gain a lot of efficiency in those cases where you have early fail, right? When you fail from the end, right? Because if you failed in the beginning, like classical brute force and Knuth-Morris, right? We maybe be able to skip a little bit ahead, but we still have to go by this window, right? We have to go through the whole string, basically, right? So this is a huge difference, right? So we gain more information, right? So very important, right? Insight. And it turns out there's many cases. So Boyer-Moore algorithm by one of the creators, right? Moore, apparently Moore, right? That's assuming that's his username, right? Assume he didn't take his co-author's name, right? So that's the basic idea, right? So we have S, right? So basically we can skip ahead, right? So again, we look at AND, right? So now we have P, right? And this is the second insight of this Boyer-Moore algorithm, right? The question is now, if we get P and this is E, right? Obviously a mismatch. Now, can we safely skip ahead all of it? Not really, because we have P somewhere in our letters, right? However, we can align it to the P, right? We could know where to align it and then start checking, right? So that's very interesting. So we know, okay, so this is not our match. We could immediately know where we should align. So in this case, 2 letters, right? We know we can align it if I skip it here, right? So this is already a match, right? right? And again, we keep going, right? So we check, okay, we check E, matches, okay. We check L, matches, okay, great. We check P, matches, of course, because we knew, of course, we know this already matches, already. So then M matches, that's great. And then, of course, we have a mismatch, A and I. And again, right, so we keep checking E, right, L, which I just did, right? P, great, M. So 4 matches. And now we have a mismatch, right? So I does not match anything. And another thing is that I actually is not present in our example needle, right? So again, right, we could shift the pattern down, right? But we can do better. We know that MPL occurs in the text, right? So we can shift the pattern, right, with its last occurrence in the pattern, which is partly imaginary, right? So, so we can pre-compute the shifts. Again, so this is going to get a little bit deeper, so we can have another alternative, right? So let's make a move. So basically, right, we can know how far we can shift because we have done this here, right? So we basically shift. Okay, we know where we could start now. So okay, this is okay. We process E already. We process 4 characters here, right? So we process E. We know, okay, where could we start our next example? We start at E here. On, that's where we check, right? And now we start checking, okay, E and P does not match. And then we go again to the end of it. And we're going to shift it again one more time. And of course, now finally, at the very, very end in this example, we can do it and we'll check one by one, right? And we'll get the match. So again, we can see this Boyer-Moore algorithm utilize this hard part. The biggest challenge is when we have almost match. We have an almost match, right? And we do all this work in a brute force. That's really painful. You do, 6 out of 7 match, and the last one doesn't match, and you have to do this over and over and over, right? And it gets extremely inefficient, right? You have very similar matches, right? Especially, again, this happens, again, if you have only very limited alphabet, you have like A, B, A, B, A, B, like really trivial alphabet, 2 letters, right? You can have a lot of partial matches when at the very end, you have just one character is not the right one, right? So in this example, you can see this general, I think it's kind of genius idea of actually combining a couple approaches to achieve, in the best case, well, it's not averaging, but it's for many common search scenarios, you get, I think, M divided by, I think, square root. Let me double check. What was the complexity? Let's see. Hopefully you can hear me, right? On the complexity, right? So this is Boyer-Moore. In a worst case scenario, it stays M times N, like the worst case. But it turns out it's not that often, right? So N divided by M. So M is the length of the needle. N is the length of the text, right? In this case, right? So N divided by M. So this is quite amazing, actually, right? So you beat linearity, right? You actually, right? You have sufficiently. So this will work when you have a sufficiently complex string, right? And also a sufficiently complex needle, right? So you have these patterns, right? And if it's like, you keep failing, like again, if there are only few, if you have alphabets, meaning there's some unique characters in the actual string, in the needle, right? The differ, you get a lot of easy wins, right? You keep jumping, right? Forward, right? And checking. So you jump forward, but you check from the back, basically, right? And plus, the Boyer-Moore has this extra knowledge, build this extra knowledge of what kind of matches you have to actually move it forward. Very, very cool algorithm, right? So I think I have an implementation here. Again, so we build a bad character table. Unfortunately, it will be really hard, again, with these indexes, it will be really hard to explain it, actually, the code, right? So we can check if it works, actually, right here. It should give you, right? So we have our table, right? Bad character table, right? And we should have 23. Now, last year, I did this timing, right? Again, since we RTU and we have this short text, we are not going to get any much improvement over brute force, obviously, right? Either approaches, you're not going to get any wins, right? So this again, this more and more is applicable when you have some early, you have a longer search string, and of course you have a longer text. So if I do timing here, right? Oh, I did have some random text. I tried to build some DNS, right? I have some text for what is it? Random choice. I have 4 letters. So this is DNS with like 1 million letters, right? 1 million DNS segments, right? Let me see, right? Yeah, so long random text, right? And again, if you've seen the movie Gattaca, right, which deals with like 1990s, right, deals with finding this. So can we find? Yeah, there is Gattaca actually in the needle somewhere there, actually, right? So again, we can see the movie here, right? Still around, yeah, this one here. Jude Law, what's his name? Ethan Hawke on Uma Thurman, right? I believe, yeah, Uma Thurman, right? Good movie, right? So on your to watch list, right? So now, so long run fine. So it is about 44 microseconds last time I checked. Let's see how it runs locally. 37 microseconds, right? So obviously, again, we only remember we win early. So how about my brute force, right? Time it fine needle. 3 milliseconds. So it's about 100 times slower, my really brute force approach, right? Again, our needle, well, our needle is pretty short, right? So we're not going to get any easy wins, actually, right? It's not very long. So how about there's no slicing? We get some extra. This is our completely brute force, right? This has used some help from the Python. This one is just slightly slower. This is completely, handcrafted brute force approach, right? So about 200 times slower. Now, Boyer more, and I think that last time I tried it, it was not much better than this actually here. We didn't get any win. So yeah, so well again, we beat our brute force, right? About half, but still slightly slower than actually using the Python's fine, right? So here, so this means Python's fine is quite general. So how about KMP? And what was kind of disappointing that KMP search actually was slower than either of these approaches. So it's no, it's about in between. Yeah, so in between. So again, why is this why does this beat? Well, they're all roughly in the same ballpark, of course, right? But this one is using the Python's built-in. So there's also the overhead, of course, of the string operations and what kind of low level. Again, I think fine, of course, is probably the DLL. The library is actually written in C, I'm sure, right? I'm sure this is such a low level implementation that you do the most of the work in the actual, machine code from the DLL, of course, right? So that's also explained. This will be interesting to see. Of course, that the actual fine, right, itself is quite efficient, right? So we could, of course, find it at the very end, right? I try to do some interesting tests, see if actually, yeah, we look at the very end, right? And we get our needle last 100 characters will be the needle, right? So will we make an improvement? So now, of course, even our find gets slow because it has to go through the 1 million string, right? So one millisecond, right? So question is now how bad is it going to be our needle, right? Still, I think it's still going to be roughly the same, right? Let's take a look. Shifting window, 137 miles. So yeah, still the complexity remains the same. And I try to see if I get any wins, right? So no slicing, right? And nothing really changed actually, right? So in this case, it's the Python's slowest, right? Again, we're comparing apples and oranges, so to say, right? And we don't get actually the improvement we would like to see, right, here from this KMP and also from way more, right? So this would be interesting challenge to do this something, I don't know, in Go or maybe Rust or C language to actually compare these approaches, right? So then we actually could see a really comparison. Yeah, so it stays the same, right? So yeah, it's actually is Boyer-Moore is actually underneath. Actually, I did some research on this, right? So there's Boyer-Moore, but it's actually there is actually Horsepool. There's another third guy, Horsepool, who made some additions, right? So of course, as usual, it's not just one person; it's multiple persons working on this algorithm, making some incremental change. So let's see if Stack Overflow is still alive. Actually, I wonder. Is this question alive? It's not closed. Okay, I'm still human. Yeah, this was 16 years ago. probably the discussion will be closed these days, or if it's not closed already, right? Come on. Okay, come on. Oh yeah, I don't want this. Cookies. Necessary cookies only. Okay, yeah. All right, as you know, Stack Overflow is going through some hard times, right? So yeah, mix between Harspool, right? With few on bells and whistles. You can read this here. It's actually from the right, so pretty good. Yeah, and of course it's written in C, so we can see here. Let's see. We can check this. I think I checked last time. Right, you can see how it's done. It's, of course, I told you it's in C, right? And you can see how it's done. Inline code, lots of inline, you know, probably some macros too, right? Yeah, a bunch of macros, stuff like that. And it's all inline, of course, because you need a right, a bunch of pointer stuff, right? Which I'm sure you love. But again, you can see, right? So if you need to find, you can take from here, from Python's approach, actually here, right? Pretty long, actually, longer than expected, right? There's some masks, right? Yeah, quite a bit. But of course, right? So this is, of course, doing it in C is not a recommended way, of course, because you can obviously, you know, off by one errors here would be very painful, right? Yeah, no, don't. Notice what they use. Things you're not supposed to use. They use goto, right, for error handling. No, but again, it's meant to know when to. Knowing when you can make an exception to actual good advice, right? In general code, you don't want to do gotos, right? But C has gotos, and sometimes for handling errors, it actually makes cleaner code, actually. So you jump to periodic window loop, right? So there's some labels, right? Yeah. Okay. So that would be extra challenge to see that, look at that C code. All right. Now, let's finish this. So these are the two main approaches. There is actually, I tried to do, there's one more in 1980s, right? You're going to do the timing, right? There is also Rabin-Karp, right? Again, these guys, again, both very influential, right? I don't know if they're both alive, but they use the probabilistic hashing approach. So hashing, right? So we have some text. So idea is this. You have especially if you're doing multi-pattern search, meaning you have different needles, you're gonna go through the text over and over again. So as usual, the main idea is you pay some costs ahead of time, basically. Do some pre-processing. Very common approach. Again, if you're gonna be doing something over and over, it might pay to actually pre-process something. So that's one of the key ideas, right? So a pro-process. So instead of checking one by one, right? We compute hashes, right? All substrings of the text with the same length, basically. And then you compare hashes, right? So then, right? So if you do a hash match, right? Basically, then we have then we double check, basically, right? Because of course, we hash collision, right? Again, otherwise we move on. So now, of course, the question is, what kind of hash function to use? I put a picture, made a picture of this SAH 256. But no, they don't use SAH 256, of course. If you check here, SAH 256, right? If I remember correctly, he's not there, but National Security Engine. But of course, Rabin and Karp are one of the. They used, I think, before they used different hashing functions. They worked on before, but Rabin-Karp, right? They used Rabin-Karp, right? Is the both are crypto. Okay, they're still alive. Berkeley, right? Turing Award, of course, right? And also Karp. Let me see what this is known for. Forget now. Yeah. There's a bunch of stuff. He's known for a bunch of stuff, and also let me double check on another guy. On Rabin is the one on that Turing Award. Right, and yeah, he has also a whole bunch of stuff actually. So both, but of course he has his own crypto system, and so also very influential. They're both still alive actually. So you can write him an email if you want to have some questions. Okay, all right. So so the approach is hashing approach. I think I have a very simple approach. I have not double checked the code, so we'll check it again. So we have a few more minutes, right, before hockey starts, right? Right. So no hockey fans here. Okay. Right. So, Python implementation, right? So we have a hash, right? Pattern hash. We have text hash. We pre-compute the hashes, right? And then again, we supply some. So again, of course, we haven't talked. This is more question of for hashing data structures lecture. But why do we use prime number for hash values? Anyone know the answer? Anyone? When we hashing, why do we when we create these hashes basically? Well, because if we had a non-prime number, right, we have higher chance of introducing irregularities basically, or hash values would not be well distributed as well basically, right? It's one of the reasons why I usually use a prime number, right? Not just a basic sort of basic explanation of that. Now we slide the pattern, right? So let's take a look. Let's take a look if it will work. Actually, I need to let me copy this code. Actually, I haven't checked. It looks good, but of course, it is in the, how to say, proof is in the pudding, so to say, right? Let's double check. Right, let's turn matches. Come on. I have not. This is brand new code, and I have to copy. Come on. Now Control Z. This one I have not tested. I can't copy this whole thing because maybe I'll do this. Yeah, okay, got you. Now let's do a code for this. And again, it is again n plus m, right? Now Python, and let's double check on our RTU, right? Let's check on our needle, print needle. What's our match? Print haystack, text, no, not long text, no. Text will be not long text, I believe, right? It's still text, yeah? I hope so. It's still variable, yeah. And let's print match. Print match. Okay, let's take a look. It should be 23, I think, right? Let's see if this works, right? We'll see if it works. If not, we will, oh no. Oh, right, text, oh, your needle is a little bit longer than I wanted, right? Or needle will not that one, right? So obviously, text length 45, needles 100, we don't find anything. So that's, well, that's good, right? However, yeah, it actually finds multiple matches, actually. That's very good too. That's why it's useful, right? However, let's do our needle text can stay, text is correct, but needle will be, let's do needle will be RTU, of course, right? That should make things much better. Yeah, works perfectly. So it works perfectly. Again, I imagine it's not gonna, the speed will be still the size of the text is small, right? On the size of needles also tiny, only 3 letters, right? And again, all the inefficiencies of Python loops will be just basically the dominating factor instead of actually measuring the performance, right? So again, use Rabin-Karp, right? Yeah. So that's what some of the takeaways. So Boyer-Moore, if you have easy losses, right? If you have some character is present in text but not in the pattern, you'll be able to use it. You know, if it's likely that that's the case, then you use Boyer-Moore. And again, I told you already that Python uses Boyer-Moore. Again, you get a lot of easy wins, right? So KMP is basically like very general, but better than brute force, but still slower on general case than Boyer-Moore, right? On Rabin-Karp is actually efficient. You have to find multiple matches basically in a text, right? You don't need just one match, but you need multiple matches, like we often do, right? Then this might be more efficient, right? So these are the 3 main ones. I have some extra materials for you to check, right? Again, if I checked the links, but I didn't check all of them, right? So again, there are some resource, like of course, if you know Geeks for Geeks, it's not an authoritative resource, but it might be nice, right, to practice, right? Has nice visualizations, and it's gotten much better. And also, it has 1, 2, 3, 7, all languages you could think of, all the main ones, right? So there's Python approach, there's Java, C, C++. Again, the code sometimes is not very good, but usually decent, right? So best case is N. Well, it's actually N well, not n2, but basically at the very end, you see, so I wouldn't say n plus n squared, but of course n times m actually, right? So not quite correct, right? So here's the academic resource, right? Somebody actually did work on brute force, right? So let's see if this one here, let's see, this one is actually good, decent. Yeah, okay, this is dev2, but I have to join. Unfortunately, I'll do is sign up with GitHub. What do we have? I know I don't want to do that. Let me do this here from Chrome, but I'm signed in. I'm lazy. Of course, I'm lazy. All right, so I'll sign in with GitHub. I should be able to join. I think I'm already somewhere. Yeah, so this is also not a, on where's my, yeah, it's not really, do I have to do it again? No, it's not really a good link actually, right? So not a good link. So you need to find a better link for that one. But the virtual lab, I want to find some nice visualization because the old one is apparently there's a link rot and it's gone. So this one here, animation. Let's see this one here, right? It's somewhere in India, but could be good. Be good. Yeah. And Government of India initiative, right? Let's see. 2.5 hours, right? If you have 2.5 hours, maybe probably quicker, right? You can check the visualization. Now, what else is there interesting, right? So of course, this is actually probably what you want to read if you're academically, if you want to do maybe something, for a bachelor's or something with string searching. This is the paper where you start. This actually, Knuth actually is quite readable for an academic, right? With his pedigree, all right? So now also Boyer Moore, right? And this is also, there's again, Medium, of course, is not an authoritative resource, but I believe there's actually the publication here. Let's double check this one. This is actually from the Moore, and this actually is a paper. Yeah. So no, again, and this worked, Boyer worked at Stanford Research Institute, and Moore worked at Xerox Palo Alto. Like again, in 1970s, the place to be was Xerox, basically, right? Because they just had too much money. And they just kept inventing things like, the laser printer, Ethernet, graphical user interfaces, pretty much anything, right? And of course, Xerox just could not take advantage of it, right? It all went to different companies, it spoils, right? So very interesting, right? So again, they just kept coming up with cool stuff, but just didn't know what to, the company was making too much money with from copy from Xerox machines, from copy machines. They were afraid to sort of expand their offerings, and when they did, they were too expensive and not competitive. So it's called innovator's dilemma, basically, right? When you have too much money, right, it'd be nice to have this problem for us, of course, but still it's a problem when you have this main business which throws off money. You're sort of afraid to change it and challenge it, right, by these new discoveries, basically, right? So inevitably somebody else from outside comes in, right? Again, so yeah, of course, again, Rabin-Karp is the authoritative resource, and I mentioned this in the beginning of the lectures, right? Is this book, right? Introduction to Algorithms. Again, unfortunately, I think we have maybe 1 or 2 copies here. I don't know if the newest version is up, been ordered, but it's $150, right? And this is the Bible, right? Yeah, this has everything basically authoritative in, right? So, and of course, the downside is they don't use, of course, they don't use Python or C, right? They use pseudocode, and it's sometimes kind of not very convenient to read, right? Because pseudocode by itself is not really, so if you want to do it something, right, you have to convert it to actual language. That's the downside to it. Now, yeah, so there's some other things to consider. There's AHO, right, multi-pattern matching algorithm, right? Another thing is, yes, there is a specific structures you can construct to make your search better, something like suffix trees. Another thing that's interesting is related is, of course, something called Levenshtein distance, right? Which is one of the foundations for approximate matching. So I don't know if anybody knows what Levenshtein distance is. Did you cover this? No? So basically, how many characters you need to change to go from one string to another, basically, right? So from, let's see, RTU to REP, maybe, I don't know, right? Or maybe from, I don't know, from Latvia to Lithuania, for example, right? How many letters do you have to change? So that's called Levenshtein distance, right? So how many letters do you have to add, or actually add or subtract, or actually change, right? It could be same number of letters, right? So this gives us a way of estimating how close the texts are. You know, these two different needles are to each other, right? So that's also might come into play. So yeah, so these are some extra reading materials. And again, if you find some updated links, I'll be, send me to the email me, right? Okay, so of course, as usual, so what are the main takeaways for today? Obviously, use the built-in fine, right, by itself. But however, the other takeaway from today's lecture, as far as general algorithms, is of course that you can pre-process if you have some problem, right? See if you can pre-process, do some work before doing the actual main big body of the work, and see if you can get some wins here. And second takeaway would be, of course, sometimes maybe you need to start work from the other direction. Maybe you get some unexpected wins by looking at the problem from the other side, right? Don't just go forward. Maybe it makes sense to go backwards, right? So that's the other takeaway. All right. So thank you, everyone. And next week I'll be available for consultation if there's any questions, right? But that's basically our course. And let's go to Ortus again. Let's double check what I want you to complete, right? There's some extra material about probabilistic algorithms, but by then you'll be all already too stressed about your bachelor's, right? And let's take a look. Yeah, some other things. But yeah, there's a subfield on probabilistic analysis, randomized algorithms. But we want, again, you can read this material, but it's not going to be, if you do the quiz, that's great, but absolutely required that you only do the quiz for today. So do the quiz for the string matching algorithms. Right? All right, and submit of course, the final maze solver, right? Right. And where is our maze solver? Yes, if you have missed something, or I don't know, yes, I do present an option to, let me update this actually. There is a way to raise your grade by 1 point by making a report of at least 750 words on something we did not cover, right? Meaning, if we only talked about this in the course, it's really not going to be very useful, right? And of course, I need at least 2 actual reference. Again, of course, if you use some LLM assistance, right, I need to see the prompts, right? Yeah. And also, don't just just submit pure LLM slop, right? Right? Yeah. I want to see actual effort, right? Of course, right. So that's something I would like. If you do want to raise your grade 1 point. Now let me see here. Yeah, so again, and so again, citations would be good because you already know how to make citations, right? Of course, right? You're good at those, right? So I will make this 25. So you can do this till in the end of May. All right. Okay. There we go. And thank you, everyone. Hopefully see you in some, I don't know, some other courses somewhere, right? Hope the class was interesting. All right, thank you.